Hello everyone, Xi from DDN. So today I'd like to share the progress of the project, Metadata Writeback Cache on client side. So I have been working on that project for a very long time. You might have seen the presentation that my colleague Oleg gave at Light 2018. So Oleg thought this brilliant way to improve metadata performance, and he made a very impressive prototype of Writeback Cache at that time. And my colleague Yingjin continues the work since then, and he spent tremendous effort on this project, targeting on merging the feature in Lustre 2.16. The excellent work from both of them enables me to give this presentation. So thank you both. So the first question for this project would be, why do we need Writeback cache for metadata? As we all know, cache is a key for good performance, and that's why Linux kernel has page cache, annual cache, and entry cache for file system. And in order to get the best performance of writing the data, Lustre take good advantage of cache whenever we write or read data. Page cache is helping us to accelerate the performance. However, metadata operations of Lustre is less optimal. There is currently no mechanism to cache metadata modifications. Each metadata modifications, like create a file or changing the attributes of a file, needs to go to MDT. But from the requirement side, the metadata performance is becoming more and more important, simply because applications are creating a lot of files. That means we really need to find good ways to accelerate metadata performance, no matter how hard it is. So let's take a glimpse of data acceleration mechanisms inside Lustre. We have got persistent cache, aka PCC, in Lustre 2.14, which use local storage on client side to accelerate read-only files or exclusive files. We can also use the tools of Lustre on demand to create Lustre file system on computer nodes. So Lustre on demand enables us to accelerate the file set of each running job. We can use data on MDT and that feature to accelerate the performance of accessing small files by reducing the RPC numbers. And by using an ancient feature with the name of OSD pool, we can build a storage pool based on quicker storage like SSD or NVMe comparing to the normal storage. And we use that pool to accelerate the data access of hot data. As we can see, when we read and write data in Lustre, operations are fully cached. We have a lot of ways to accelerate the performance according to the I/O patterns of our applications. We need to do similar things for the metadata performance too. A lot of applications and use cases will benefit from acceleration of metadata performance. So there are always many ways for the same purpose. In Writeback cache, we might have chosen the most difficult way, but the most efficient way. So cache could be Lustre server side or Lustre client side. Obviously, if we cache the data on Lustre client side, we will be able to get better performance due to the data locality. But client side cache means we need to implement very complex mechanisms to keep consistency between different clients. We choose to implement client-side cache, which is harder. As we said before, currently Lustre client sends RPC to MDS on each metadata modification. That is far from optimal. Thus, in Writeback cache, we delay the metadata flash as much as possible to reduce I/O latency of the application. And when metadata flash is inevitable, we flash the metadata in batch. That will reduce MDS innovation of metadata modification. But at the same time, we will need to implement mechanisms for batch flash and space reservation, and that's complex. And in order to maximize the performance, we use volatile memory to cache the metadata instead of persistent storage. That means we need to introduce complex mechanism to reduce risk of data loss. And most importantly, we want to keep strong POSIX semantics of Lustre. Loosening semantics might make things much simpler, but that would not be friendly for applications. Thus, we choose to use complex LDLM log protection to keep the strong POSIX semantics of Lustre. And after doing that, all the applications can benefit from this new writeback cache transparently. We do not need to change the application. So this diagram shows the general idea of Lustre writeback cache. So Lustre has a lot of clients. Each client might cache different parts of the directory tree, and when these cached files are cached in my writeback cache, the tree will purely be controlled by the local client, and no RPC will be sent to MDS. The cached tree will not be flushed to MDS until remote access from another client is accessing the tree, and the flush will be batched, delayed, and aggregated. That would be the major reason why metadata performance can be accelerated by this new feature. So let's take a deeper look at the design of writeback cache. Obviously, we do not want cache the whole directory tree on the client. Writeback cache provides policies based on user-defined rules to control which directory to cache on the local memory. Administrator can define rules based on UID, GID, project ID, and file names to control the behavior in a very flexible way. And when it is decided that the directory tree will be cached on the client, an exclusive LDLM log will be acquired for the root directory. After holding the log, all the metadata and data can be cached on this client safely. No RPC is needed for any operation of the whole directory tree, including metadata and data modification and access. So inside the Lustre writeback cache, we use a data structure with the name of memfs to manage the cache data and metadata. And memfs analyze the inode cache, directory cache, and the page cache in VFS as its data structure. So we use a lot of existing data structure in the Linux kernel. The cached data and metadata will eventually flush to Lustre servers, but we want to delay that for better performance. The flush happens in several cases. First, when there is remote access of the directory tree from another client, the flush needs to happen. And second, as we can see, if the local host is having memory pressure, we might need to flush the cache to release some memory. And third, in order to reduce the risk of losing data, writeback cache will flush the data periodically, for example, every 5 seconds or 10 seconds. As said before, writeback cache flushes the metadata in a very efficient way for the best performance. It flushes a batch of metadata in a single bulk RPC, which used to cost hundreds of thousands of RPCs, and that improves the performance a lot. I mean the batch RPC. This diagram shows the components of Lustre writeback cache. As we discussed, writeback cache will not change any interface of VFS to keep both POSIX semantics. So it uses existing entry cache, inode cache, and page cache, and uses these structures as its own for its own data management. And besides of these, writeback cache has interface for connecting to PCC, aka persistent client cache, that will provide further improvement of performance. And we will discuss that later in this presentation. So for any cache system, the mechanism of cache management are always complex, or the corner is the corner of the cache system. And for writeback cache, things are even more difficult because Lustre is a distributed system. Thus, writeback cache use quite some state flags of files or directory for the purpose of cache management. The first one is WBC root, which means the directory is the root of the cache tree. For WBC root, an exclusive LDLM lock will be acquired to protect the whole tree. And WBC protected is a flag that means the file or directory is under the protection of an exclusive LDLM lock, either directly or indirectly. WBC cached is a flag that shows whether the directory and its children are fully cached in MFS. If the flag is set, all the metadata operation go to MFS. If not, the metadata operation needs to go to MDS. WBC flash is another flag, and that flag shows whether the metadata has been flashed from MFS to MDS. And we also have WBC assimilated. That is a flag that shows whether the page cache has been assimilated from MFS to Lustre OSC. So there is obviously a special meaning of assimilation. So we will check the meaning of that later. So in several different cases, the state of files in writeback cache will change from one to another. And these are three major operations for this change of states. That is WBC purge, WBC assimilate, and WBC flash. So WBC purge means purging the WBC root from the writeback cache. It happens when remote client access a WBC root, and when that happens, WBC root will flash the metadata and release the exclusive LDLM lock, and then it becomes normal Lustre directory. And after that, the children under that directory get exclusive LDLM locks and becomes new WBC roots. There is another process with the name of WBC assimilate. It means assimilating the data from WBC to normal page cache of Lustre. So it happens when we need to release some memory from the cache. When it happens, the metadata of the file and its ancestors needs to be flashed first, and the data will still be cached in page cache of Lustre client, and it will not be flashed to OSS and immediately, but eventually it can be flashed to OSS like normal files. Another process is WBC flash. It will flash the directory from WBC to MDS, and the directory will not be fully cached anymore. So this happens when we need to create a file under the directory, but do not have any more memory to cache. And in order to simplify the implementation of writeback cache, this WBC flash process will happen too for the when renaming or creating hard links inside writeback cache. But this can be improved in the future. So we will be able to keep the files inside writeback cache, even so we need to do renaming of creating hard links. So when the WBC flash happens, this directory and its children needs to be flashed to MDS, and the WBC cached flags will be removed from these files. This diagram shows example of these three operations of state transitions. We can see how the status change under these three cases. And the state transition change is important because writeback cache depends on the state for cache management. This diagram gives an example of how state flags change when purging the writeback cache root. As we can see, the root of the cache tree changed to normal Lustre directory, and the directory of the former root becomes new roots. And that's simple. The diagram shows how state flags change for WBC flashed operation. Writeback cache flashed the metadata of a directory and its children, and the writeback cache will not cache them anymore. So when we access that, we need to access that from MDS rather than the cache. So this diagram shows how state flags change for WBCS simulation operation. After WBCS simulation, a file of the page cache of a file will be managed by normal Lustre mechanism, not writeback cache anymore. So the data can be flashed to OST when we need to. Okay. So after understanding the design of writeback cache, I think it is obvious why writeback cache can accelerate metadata performance. One major reason is it flashes metadata of files in batch that greatly reduce the RPC number of operations. And the batch metadata operation can be used for other purposes. For example, it can be used to accelerate operations like deleting the whole directory tree, and the acceleration will be huge, as we can see. And another reason of metadata acceleration is writeback cache can aggregate metadata updates. Only the final state of metadata will be flashed to MDS. For example, if we create a new file and we do some operation on that file, we change the mode or change the attribute of the file, and eventually we remove the file. So when we flash the tree to the MDS, the file is gone, right? And it looks like it never exists to the MDS. So that means we do not need to flash the data or metadata to MDS. And the MDS never knows that file exists. And that reduces the total number of MDT updates. And one ongoing feature that ongoing development that the engine is working on is to combine writeback cache together with PCC. By doing that, data will still be cached on client-side PCC, even if there is not enough memory to cache the data on in the memory, and that also means we could save more memory for caching the metadata, and it will accelerate. More memory will accelerate the performance further. And another interesting feature that we are looking at is using writeback cache to support offline or disconnected clients. This new feature might be useful for use cases like Lustre on internet or Lustre on a very different network condition. So currently, Lustre writeback cache is still under very heavy development, but at least it is stable enough or mature enough to run several benchmarks. One benchmark that we run is to compress the Linux kernel, decompress Linux source code turbo. And as we can see from this diagram, comparing to TempFS and EST4, the decompressing speed on Lustre without writeback cache is not super optimal. It is not very surprising for a network file system, because depressing a turbo means creating a lot of small files, writing a lot of small data. So Lustre does not have the best performance, but at least Lustre is doing much better than NFS. As we can see, for writeback cache, the performance is not bad at all. So writeback cache is really suitable to be used for these kind of applications. Performance have been increased for about 8 or 9 times. And I think it is safe to say, even comparing to local file system, the performance of Lustre on writeback cache for this benchmark is not unbearable. It is reasonably good. So this diagram shows the traditional MD test result for different network file systems. It is very obvious that writeback cache brings the performance of all metadata operation to a totally different level. With writeback cache, the metadata performance of Lustre do not look like a network file system anymore. This graph shows the metadata performance of Lustre Writeback Cache, and it compares with local file system to understand whether the implementation or internal mechanism or internal data structure is efficient enough. After looking at the detailed number, I think it is safe to say that the efficiency of the data structure of Lustre Writeback Cache is not bad at all. It's only a little bit slower than TempFS, and I think TempFS is pretty much the ceiling of all possible implementation of file system. So as a simple conclusion of the presentation, my colleagues developed a very nice feature with the name of Writeback Cache, and the result shows that as long as the application has enough locality of metadata operations, Writeback Cache will provide very good performance. And I believe a lot of applications will benefit from these upcoming new last features. And I'm already looking forward to that feature. And that's all for my presentation. Thank you very much.